Hello, my name is Rafael Saavedra, and today I'd like to talk about joint work with Christopher Zhang on the finite blocking problem and periodic points on the regular n-gon and double n-gon. Our work deals with a dynamical system called dynamical billiards. As the name suggests, this system can be interpreted in terms of the game of billiards. Consider a polygon like this L-shaped polygon that I've drawn here. This is going to be our billiards table. We can pick a point, like the one labeled A, where we place a billiards ball and launch it in some direction with a uniform velocity. For example, in the direction of this gray point over here. Once we launch the billiards ball, we see that it will bounce according to the rule that the angle of incidence equals the angle of reflection, and it'll eventually, after bouncing several times, reach some other point, B. There's another way of interpreting this system, which will also be useful later. Instead of thinking it as a billiards table, we can suppose that this polygon is a room where the walls are mirrors. And instead of having a billiards ball, we light a candle over at point A, which will send out beams of light, which will then bounce off the walls because they're mirrored. With either of these two metaphors, we can see that there's some complicated behavior in dynamical billiards, such as that which is illustrated in this example. As a result, there are lots of interesting questions about the complicated billiard trajectories in a room like this one. One of the questions that I'm going to be talking about today is called the finite blocking problem. Suppose we have a billiards table and 2 points A and B. The blocking problem asks, is there a finite set of points S called the blocking set, such that all trajectories from A to B pass through S? That is to say, can we block the billiards ball from getting to B from A by placing obstacles at the points of S? In the example I've drawn here, for these points A and B, we see that the straight line from A to B passes through the center of the polygon labeled X. This point X will block this particular trajectory. However, it's not clear whether A and B are finitely blocked, because there could be other, more complicated trajectories that bounce around the walls of the polygon and eventually make their way to B. And we don't know whether we can block these with only a finite set of points. However, there is one insight that allows us to see that these complicated billiards trajectories are not as complicated as one may first think. The idea is that of unfolding them. Let's start with a simple example, a right triangle with a pi over 3 and a pi over 6 angle. Suppose we have a trajectory inside this triangle. We want to unfold it. How? Well, let's think back to the illustration of the room with mirrored walls. When we look at a mirror, we know that we're just looking at reflected light, but it looks to us as if there's actually another world on the other side of that mirror. Let's take this fantasy seriously and think, what if instead of bouncing off the mirror, a ray of light actually went across into the other room? That is, if we begin with our original triangle, and starting from point A, go along the red line segment until we hit this side of the triangle, we continue across a reflected copy of the triangle onto this green line segment. We can now see that the billiards trajectory, which in the original triangle on the left was complicated and switched direction with every bounce, now unfolds to a straight line that goes from the initial point across the red, then green, then blue, and then purple line segments. At each point, when we hit the side of the triangle, we simply make a reflected triangle and continue through it in the same direction. At the very end of the purple triangle, however, we can also do this, but we will get a triangle that is a translation of this one up here, where we have the orange line segment. And so it doesn't really matter where we put that triangle, as long as we keep track of the fact that this side of the hexagon is glued together to this bottom side. What we've gotten is a hexagon with opposite sides glued together. This is an example of a translation surface and of how we can unfold a triangle to get a translation surface. In general, a translation surface is a surface obtained by gluing pairs of sides on a polygon by a translation. That is to say, when we go through one of the sides and come out the other side, we are not rotated or reflected, we are just translated. And a translation surface will be a surface just like a sphere, a torus, or a torus of higher genus. However, because it's represented by a polygon in the plane, the coordinates of the plane will give the surface a flat metric except at the vertices, where there are singularities. In order to represent a translation surface, we use the convention that opposite sides on a polygon are glued together. So for example, in the bottom left, I've drawn a square. This specifies with our convention a translation surface called the square torus, because opposite sides of this square will be glued together. In the center, we can see a translation surface that will be a cover of the square torus, and on the very right, we see a translation surface which will be the central topic of the rest of the talk. It's one where we have a regular polygon with opposite sides glued together. Now, we've represented translation surfaces with polygons, but the same translation surface can be represented by more than one polygon. We say that two translation surfaces are isomorphic if we can obtain one from the other by cutting along straight lines and regluing via translations. For example, looking at the very left, we have a parallelogram with opposite sides identified, which I have also colored to make it clear. If we cut along this green line segment in the middle, we get two triangles, which we can then slide past each other and reglue, where we've reglued the red side over to the red side on the other side. This gives us a square, and in fact, this is the same as the original square torus. This shows that even though the original parallelogram isn't a square, it still represents the same translation surface. Now, let's go back to our original motivation for translation surface, which was that if we had a polygon, we wanted to unfold it. In general, a polygon, all of whose angles are rational multiples of pi, unfolds to a translation surface. It's important that they be rational multiples because otherwise the unfolding won't terminate. The blocking problem for billiards then reduces to the blocking problem on a translation surface. We ask, can all the straight lines from A to B on the translation surface be blocked with finitely many points? Well, let's first look at an example where there is some kind of blocking. I claim that for any 2 points A and B on the square torus, they are finitely blocked by exactly 4 points. To see this, we can look at the universal cover of the square torus. We have here 4 representatives of the point B in the universal cover. All the straight lines from A to B inside the square torus will unfold in the universal cover to straight lines going directly from A to a representative of B. If we want to block all these trajectories, we can try to choose the center midpoint of all of these line segments. These midpoints, for which the equation is given here, there will be infinitely many of them. However, once we project down to the square torus, they will project down to one of these 4 points, which I've also drawn in this diagram. As a result, all the trajectories from A to B, even though there are infinitely many of them on the square torus, will be blocked by only 4 points, which I've depicted here and labeled from x1 to all the way to x4. Now that we've seen this example of where there is blocking, let's look at the problem that I worked on over the summer with Zhang. Chris and I looked at 2 translation surfaces, called the regular n-gon and the double n-gon. Let's look on the left. We have a regular polygon with n sides, where n is even and greater than or equal to 8. Because n is even, we have opposite pairs of parallel sides, which we can glue together to get a translation surface. We call this the regular n-gon translation surface. If n is odd, then there aren't opposite pairs of sides. So what we do, as we can see on the right, is we take a regular n-gon and then glue it to another copy of itself, and now we actually do have opposite pairs of parallel sides, such as this one on the upper right and this one on the lower left. This is what we call the double n-gon translation surface. In our work, as I'm going to explain later, we solve the finite blocking problem on these translation surfaces. And as a result, we obtain information about finite blocking for billiards. The reason is that the triangles whose angles I've given here, and which I've also drawn inside these polygons, will unfold via the construction I described previously to either the regular n-gon or double n-gon translation surfaces, or a finite cover thereof. As a result, we can solve the finite blocking problem for the billiard dynamics on these triangles by solving it for the translation surfaces. Before I go further, it's important to note that these two translation surfaces have an important symmetry. It's called the hyperelliptic involution, and it's the map that rotates these two translation surfaces by pi radians around their obvious midpoint. The importance of this involution is that it's central for the kind of blocking that occurs on these translation surfaces. In 2017, Apisa and Wright proved a general theorem about finite blocking on translation surfaces, which, when we specify it to our case, almost solves the finite blocking problem. It tells us that on the regular n-gon and double n-gon translation surfaces, the only pairs of points that are finitely blocked are either a point and its image under the hyperelliptic involution, in which case the blocking set consists of periodic points of the translation surface, or pairs of points which are singularities or periodic points of the translation surface. Now, I haven't defined what these periodic points are, but they're very special points associated to a translation surface. And it's precisely finding out what the periodic points are that is the missing step towards solving the problem of finite blocking. This is what Chris and I worked on over the summer. Now, in order to define what periodic points are, we have to talk about affine diffeomorphisms. An affine diffeomorphism of a translation surface is a homeomorphism which is affine in local flat coordinates. Because our translation surface is in the plane, recall that we have local coordinates coming from the xy coordinates on the plane. As a result, if we have a homeomorphism which is affine in these coordinates, we call this an affine diffeomorphism. For example, for the square torus, the transformation that gives us this parallelogram, which we've already showed is the same as the square torus, this is an affine diffeomorphism because in coordinates, it's given by this matrix. Similarly, the hyperelliptic involution, which I already described, is an example of an affine diffeomorphism because in the coordinates of the plane, it's given simply by a rotation by pi radians. We say that a point on a translation surface then is periodic if its orbit under the affine diffeomorphism group of the surface is finite. During our project, we were able to show that the only periodic points on the regular n-gon and double n-gon translation surfaces are the red and gray points below. For the regular n-gon, it's the center of the polygon, the midpoints of the sides, and these gray singularities. For the double n-gon, we have the midpoints of the sides and the gray singularities. As a result, we get some corollaries about finite blocking. We can deduce that the only blocking on the regular n-gon and double n-gon translation surfaces is between a point that is not a singularity and its image under the hyperelliptic involution. For example, for this regular n-gon here, we see that the trajectory going straight from A to B is blocked by the point x, but our result tells us that A and B are actually finitely blocked, including for all the other possibly infinite number of trajectories going from A to B that we haven't drawn in the diagram. This, as I described previously, has consequences for finite blocking in billiards. When n is even and greater than or equal to 8, we showed that the only blocking on this right triangle, which we talked about previously, for billiard dynamics is between the pi over n vertex and itself. In the case when n is greater than or equal to 5 and odd, then there is no blocking on this triangle. Now, I'd like to say something about our methods. Veach calculated the affine diffeomorphism group gamma of the two translation surfaces. Based on this, it's easy to show that all the points that I mentioned previously are periodic points. Chris and I were able to show that all other points had infinite orbit under gamma and thus couldn't be periodic. This is hard because for any particular point, we have to exhibit some infinite orbit under the group gamma. We were able to show this by relating the action of gamma on the translation surface to a second group action via what we call the transfer principle. In full generality, the transfer principle applies to two commuting group actions. Suppose that a group G acts on the left on a space X, and a second group H acts on the right. Then G will act on the left on X mod H, and H will act on the right on X mod G. The transfer principle tells us that the G orbits of X mod H are in bijection with the H orbits of X mod G. In our case, we can let the affine diffeomorphism group gamma act on the left on the group SL2R, while we act on the right by the unipotent subgroup U consisting of matrices of this form. The action of gamma on SL2R mod U is related to the action of gamma on the translation surface. Meanwhile, the quotient SL2R by gamma will be the unit tangent bundle of a hyperbolic surface, and the action of U on this manifold is the action of horocycle flow, which is a well-studied flow in hyperbolic dynamics. By appealing to results about the orbits of horocycle flow, the transfer principle then allowed us to classify the orbits on the translation surface by the group gamma. Once we classified these orbits, we applied affine diffeomorphisms to representatives of these orbits to show that they had an infinite orbit under gamma. And as a result, we showed that all of these points could not be periodic. Now, if you have any questions about this work, then I'd be very happy to answer any questions over email. I believe that my email should be listed in the abstract for this talk. If you would like to read more about this and about rational billiards in general, I suggest the survey by Alex Wright titled From Rational Billiards to Dynamics on Moduli Spaces. And if you would like to read about billiards and blocking problems in specific, I suggest the work of Apisa and Wright, which I cited earlier. Finally, I would like to acknowledge the support and the organization that went behind this. Chris and I would like to thank the organizers of the University of Michigan REU, where this work was conducted. We would also like to thank Alex Wright and Paul Apisa for organizing the project on translation surface, and Paul Apisa for mentoring this project in particular. We acknowledge the support of the National Science Foundation, which funded this work through 2 grants. And finally, we would like to thank the organizers of the Young Mathematicians Conference for this opportunity. Thank you for listening to the talk, and hope you have a nice day.